All right, let's go. Ooh, good. I'll try to start. Ready to go. Yeah. It's a career first to be late for my own talk. And then I realized the advantages as I was making my way here, because I realized if I was late for other people's talks, they wouldn't take it personally. There are all kinds of advantages. Can I have a clicker for the good. Okay, so since I have missed a bit of time, I'll probably skip a few slides. So the real issue here is, let me just skip, actually, let's skip some stuff. Skip on. Well, there are some examples here, but we don't need to talk about AlphaFold. Boring. Everyone talks about that. Now, when I used to talk about AlphaFold, it was exciting because there hadn't been a Nobel Prize, but now sadly there has been. So really this talk is about what's inside predictably successful, including the title, deep learning models. And of course, there's this traditional argument in the philosophy of science, which goes like this. When a theory is empirically successful, in particular when it issues in a lot of novel predictions that are correct, what explains that? And the standard answer is the approximate truth of the theory, or this is probably the only half-decent argument for realism. People differ about how good it really is, but it's some kind of argument. So having realized that this argument exists, one might naturally ask if there's something similar in the case of an AI system when it's predictably successful. And it surprised me when I had this idea that no one else had published a paper on this, because it seems so obvious once you think about it. I was very happy to get the first paper published on this, suggesting that, yes, you can extend it to AI systems. And that was a paper in Synthase. So what I'm going to start by doing is outlining the work that I did on that with a couple of postdocs working with me at the time. And then I'm going to, be entirely self-referential and criticize my old work somewhat. There are two criticisms I think I have of it now, and I wish I'd had this better idea instead. Mind you, I mean, sometimes it's good to have the better idea later because you get more publications. I promise I did have the idea later. Honestly, I would never deceive. So then what I want to do is develop a new and superior AI-specific numericals argument as a result, responding to these criticisms, and it appeals to this novel notion of quasi-representation instead. And then I want to briefly consider the implications for XAI, and I'm going to use GraphCast as a case study, which I think in many ways is more interesting than AlphaFold 2, which is the case study we've used previously. The quick reason it's more interesting is because AlphaFold 2 has been tinkered with a lot in the various modules, and it's been specifically designed in certain parts to ape traditional scientific activities. GraphCast, it's nothing like that. It's nothing gerrymandered in it, which is really interesting, but it's incredibly successful. Okay, so the standard numericals argument features this central claim: empirical successes in science enabled by scientific theories are non-miraculous because such theories are typically or probably approximately true. So we're just going to focus on novel predictions because people can differ in their opinions about what empirical success really amounts to. There's this old debate about the value of accommodation rather than prediction. And then various people have distinguished between different forms of prediction too. Exciting stuff. So this is a standard NMA in the local variant. By local variant, I mean it works for one theory you can pick specifically in isolation. And of course, the first premise is just that the probability that it's empirically successful, if it's approximately true, is high. The probability it's empirically successful, if it's not approximately true, is low, being the second premise. And then therefore, this is supposed to be a deductive argument. It's going to follow that the probability that the theory is approximately true, given that it's empirically successful, is high. The only problem with this argument, it's a pretty big problem when you apply it to one thing, is the base rate fallacy, which we should be aware of from things like medical tests, right? If I go and get an AIDS test and it says positive, I'm HIV positive, I shouldn't just look at the false positives rate. I should also look at the amount of people in the population, the frequency in which the disease exists in the population, because actually a lot more people are going to get false positives than people are going to get true positives, just because it's not that common a problem, certainly in some parts of the world. Okay, so the answer is you can circumvent this problem somewhat. it seems, by instead considering larger groups of theories or perhaps the whole of science. So a lot of early work on the NMA was a bit vague about this, which version they were really thinking of, but you can make this shift. I'm just turning the screen off. It's not what I want to do. Wrong button. So you can instead go to this global variance. I'm not going to say much about this. I just put it in for completeness. We're going to consider a global variance. So we consider the relative frequency of empirically successful theories in the domain we're considering. It turns out that if you put numbers in, that little r there doesn't need to be that big. You can put in some plausible numbers for the other things, and you get little r at about 0.3, and then you can get the argument to run. For example, I have some numerical examples worked in the first paper. Okay, so now we want to bring this traditional NMA across to AI. What are the potential obstacles? There are three obvious ones. First of all, it's dubious there are truth bearers present in AI systems, right? There might not be anything propositional in there. Secondly, it's actually questionable whether there are representations at all in an AI, at least ones that are independently formed. It's not controversial that you can take the inputs and outputs often to be representations, but it's much more controversial that you can take things that the AI generates itself internally as representations. And indeed, many philosophers have said that there are no representations in AIs. So then even if you imagine that they're present, the representations are there, the third point is that, well, are they theories, right? Are there theories in the system? Because the NMA seems to concern theories. So what I want to do now is just briefly address all of these. I'm going to run over what we say about these things in the paper. Does the no Milker's argument apply to AI? I'm not going to go into too much depth about them. I'll be pretty quick because the new version of the NMA I'm going to present circumvents the first two problems quite neatly. And the third one, I mean, they're not, in a way, they're not really problems. I think that I still think the responses are pretty convincing, but sometimes you want to just go with your potential critics quite a long way and see what you've got left. Okay, so first of all, look, I think we can use representational accuracy or accuracy as a substitute for approximate truth. You don't have to, I mean, the quick argument is just that when you think some descriptive statement is true, it's precisely because you think it's an accurate representation, say, of a state of affairs in the world or in some possible world. That's exactly what makes it true on a very traditional view of truth. So that's okay, right? Unless you have a really unusual view of truth. Most people in the literature on scientific realism, at least, tend to just pretty much accept something like a correspondence theory of truth for the sake of argument. Actually, I don't particularly subscribe to that view, but you know, you have to have some common ground to have a fruitful debate often. Okay, so I really think this objection is really not particularly interesting. It's dealt with very easily. You know, similarly, I mean, you can look at a map and you can think that a map accurately represents various things. You can think that there are various propositions that are derivable from the map, but they're not actually, you know, directly stated on the map. For example, that Sai Kung is is quite a fair distance away from HKU, and I mean, the traffic jams aren't represented on the map. But okay. So you don't need to deny that an AI can contain propositions, but even if it doesn't matter. You can still have accurate representations, potentially. If you can have representations at all, that's the second problem. Is it the case that an AI can create, embody, or imply scientific representations? You might think not. And this is a theme we're going to come back to, because at least the extant accounts of scientific representation tend to involve agents and their intentions, but of course, at least narrow AI systems of the kind that we deploy now, narrow deep learning models, they are not agents, except sense of a very strained analogy. So for example here, I mean, often the reason that agents are typically introduced is to break symmetry. So, you know, if I take a photograph, like Geary has a similarity-based account. If I take a photograph of Frank here, Frank doesn't represent the photograph, but the photograph will represent Frank. I am a good photographer, don't worry. Okay, so to break that asymmetry, in the case of scientific models, at least, he appeals to the attentions of agents or agents. The quick response to that is that, well, you don't need intentions, you just need intentionality, and you don't want to conflate the two things. So you can appeal So argue in the previous paper just to naturalistic theories of mental content and mental representation, which of course the idea there are mental representations is very standard in contemporary psychology and neuroscience indeed. Okay, so if you think that there are mental representations in the case of humans, why would you not think an AI can have them too? This is actually a really interesting topic, and I could say a lot more here. There's some really fascinating empirical studies, for example, on bees. It turns out that bees can, the quick version is they can see that they can feed effectively from spherical objects rather than cuboids. They can only see the objects though, right? They can't touch them. And then you put them in an environment where they can't see the objects, but they can only touch the objects. And they actually work out very quickly that it's the spheres just by touch that they want to be feeding from. You can also run it the other way around, starting with the touching, and then you only give them the vision afterwards. And you can also control for the fact that put them in the same scenario where they can't touch. There's nothing else they're using to put their proboscis into the correct holes, right? So this is a good argument. It seems one of the best arguments that bees have mental representations. And then from that, you can think, well, bees don't have that many neurons, right? In fact, we can create AIs with more neurons than bees. So then you're going to get into, well, do you think that something like its backpropagation is a mechanism that's going to stop them having mental representations? And actually work is ongoing with that in the empirical sciences too, right? It's actually just a paper published not long ago, still in the process of reading, arguing that something like backpropagation does actually happen in animal brains. Okay, so of course, these theories are compatible with AIs representing parts of the world. Very quickly, the idea, of course, is that you can give a complete causal account of how the system behaves without appeal to semantic properties, but those properties become relevant when we want to explain how the system interacts with its environment, particular kinds of covariance, for example. Okay, so you might say in the case of AlphaFold 2, for example, it's reasonable to conclude that it contains representations of some physical laws or models. Of course, when you want to look at the architecture as well and the way that the system was set up. So you wouldn't want, I think, to say that AlphaFold 2 has any representations of the dynamics of protein folding, but it's much more plausible it has some kind of representation of laws that govern what count as the most energetically favorable fully folded states, right? At least tertiary structure rather than anything beyond that. There are quaternary structures too. Course. Okay, so that's B, A and B. C is very interesting. So, you could say, well, okay, there might be something in AlphaFold 2, but is it a theory? And I think here, the problem here is that people, when they talk about the normal NMA, are pretty lazy and don't think carefully enough, and they shouldn't ever have said theories to start with. That's the basic response here. As Duhem memorably pointed out, Duhem's notorious thesis, which goes not only for physics, as he thought, but plausibly many empirical sciences. You can't test a hypothesis in isolation, but only a whole theoretical group. Come up with toy examples really easily, like, if I let go of this pointer here and it floats in the air, have I falsified Newton's first law, which says that everything remains at constant velocity unless there's a resultant force acting on it? No, you can't tell, because that by itself doesn't give you any way to determine whether forces are present or not, or what forces there are. Right, so simple case. And so the problem goes on. There are no crucial experiments, as Duhem put it. And that's really interesting. I mean, the Leverrier story is particularly interesting in this case. One thing I don't talk about here, I mean, basically Leverrier faces the same scenario twice. Unexplained orbits. The first time the unexplained orbit is of Venus, and he predicts the existence of Neptune. Incredibly thorny, hard problem, which is remarkable. And this is thought to be the greatest success ever of Newtonian mechanics at the time, or classical mechanics, I should say. I mean, it's very lazy to speak only of Newtonian mechanics, because there are all kinds of very useful. I mean, there's no strictly speaking differential formulation, for example, in Newton's work. So classical mechanics, which was, of course, contributed to significantly by Newton. So the first time you find Neptune, second time you get the aberrant orbit of Mercury, the precession of the perihelion, and you try to do the same trick. You're like, oh, well, there must be another planet called Vulcan. And of course, people spent a lot of time looking for Vulcan. Many people claim to have found Vulcan. Of course, everyone wants to be the first to spot a new planet. but there is no Vulcan, it seems, except in Star Trek. Sadly, it would be nice to meet Vulcans. And the point here is that in that case, it seems like you needed relativity to account for the discrepancy between the predictions and the actual orbits. Okay, so same scenario. And in one case, you blame one part of the predictive machinery. In the other scenario, you blame another part of the predictive machinery. Right? You can blame the model, you can blame the laws, initial conditions, many different things can go wrong. That is the short version of this. I'm going through it all. So of course, it's hard to deny that the discovery of Neptune was a massive scientific success. But you have to really, to make something like an NMA plausible in this case, you need to think about the machinery as a whole and the approximate truth of whole of that. If you just pick out one item and say like, oh, well, it was the laws of classical mechanics that were responsible, that seems entirely arbitrary, because you could actually in principle run the same argument for the other components too. And one of the things that he used actually was the Titius-Bode law, which is quite false, but helped him a lot. I mean, there were actually so many unknowns in the inverse perturbation problem. It's kind of, I mean, I still wonder if he didn't just get lucky. It's an interesting case. Okay, so an approximately true proposition might issue multiple new truths when combined with an array of propositions that fail to be true, but the probability seems low. Final point. Okay. So we want a holistic view of the NMA, and the crucial point is just that we should never have considered the NMA to be narrowly in terms of laws or theories. Of course, what theories are, I mean, you know, go down that rabbit hole, but at least one traditional view of what theories are is syntactic, and is things like all statements or statistical laws. Then there's also of course, the semantic view of theories, which I didn't mention earlier, but could have, because of course, on the semantic view of theories are never, strictly speaking, true or false, or therefore approximately true. So you'd have to revise your NMA if you had a semantic view of theories too. But people just don't do this. They're kind of a bit lazy in the way they set it up, it seems to me. Okay, so we want the NMA to cover a broad range of representational machinery if it's going to run at all. Otherwise, it just seems like you're picking out something from the things that you've got the success with arbitrarily. Okay, so recap. Representational accuracy can take the place of approximate truth. There are naturalistic accounts which explain how a system could accurately represent, even in the absence of an agent and/or their intentions. And the representations in AI systems may be correlates of a wide range of representational machinery, not just theories or hypotheses. Okay, so here's the original AI-specific NMA we came up with, and you know, it's just making the changes that I just went through. The probability that an AI is empirically successful, given that it accurately represents its task-related empirical targets, is high. There's still the F thing in the background, of course, because we don't want to commit the base-relic fallacy. And then the probability that it's empirically successful, if it doesn't accurately represent them, is low. And then we get the conclusion here, comes out nicely. It's a deductive argument, provided that little f is set correctly. Okay, so in the case of something like AlphaFold 2, so Skolnick and et al. Remark, you know, it seems to work by magic, input a protein sequence, primary structure, and by magic, the protein's three-dimensional structure appears. But if the AI-specific NMA is sound, then there's no magic, no miracle. Two warnings about AI-specific NMAs are worth making, though. First of all, notice that you can't account for something like AlphaFold 2's success by appealing to its training history. There's like an evolutionary argument that Van Fraasen makes as well. Bad argument, because it changes the topic, right? What we want to explain is what property those theories have that makes them successful, right? So you've got a theory, you found it, however you found it, that has this property of being empirically successful. What explains it? Or what explains why that group, if we're doing a global argument, why that group that is successful, what marks them out as special once you've got them? It's not about the selection process, right? I mean, you could find a great tennis player by picking out the winner of Wimbledon. And then when you ask, why is he a great tennis player? You want to say, well, it's because he won Wimbledon. That's silly, right? You want to look at his mental strength, his physical ability, his flexibility, his speed, all of those things. So that's important to note. You could run an anime for a swamp, like Swamp Man, Swamp AlphaFold 2. It appears on the servers. Why does it work? What is it about that? Saying it came from aliens doesn't help, right? It's like, yeah, but what did those aliens, come up with? Okay, and second, I didn't argue that the standard anime is sound, and we never did. The point of the argument is just, look, the idea is kind of like they stand or fall together. If you believe in the traditional anime, then why don't you believe in this too? So it could even be a reduction of the traditional anime. If you think for some reason it's bad, maybe you could get a reduction of that. Okie dokie. But I think it has two problems. First of all, it involves an inference to the presence of hidden. So even if you admit that there can be representations, our argument was just that there can be representations in AI, it's a bit different to infer to their presence in any particular case. In the traditional case, we've got the theory, right? We can look at the theory, there's the theory, and then we're just ascribing a property to the theory, approximate truth. In this case, we're saying there's something we can't see, and we're ascribing a property to it. Okay, it's more like two steps. So therefore, this is going to make it less plausible. And second, this is a slightly more subtle point, but I think it's interesting. Someone might say, well, yes, but your argument that representations could be there just preceded by analogy to mental representations, and we're interested in scientific representations, right? So maybe you could doubt the anime truly extends to AI systems because the traditional anime concerns scientific representations, and the AI-based variant doesn't. It talks about instead mental representations. Those could be somehow interestingly distinct in kind. Overall, I guess I suspect that probably the reason that a lot of our historical accounts of scientific representation talk about agents is because they didn't really think much about AI when they were designing them. I have to be honest, but that literature hasn't caught up. So that's what we have to deal with. Okay, so what's the response? Well, let's start with accounts of scientific representation and abandon the requirement that there are independently formed representations inside machine learning systems. And then I think by starting and considering those, you can develop a more defensible anime, which instead rests on the notion of quasi-representation. So what are scientific representations? There are three extant accounts: similarity-based, structural, and inferential. Let's briefly have a look at each. So here's a basic version of the similarity account. A model represents a target if it's similar to that target in relevant respects, and it's about that target. So what makes it about that target? Well, as we already saw, Gear's answer requires bringing scientific agents and their intentions into the picture. Again, remember, the idea is to break the symmetry. Okay, representation relations are asymmetrical. Similarity is normally taken to be symmetrical. I mean, there are actually some people who argue it's not, but it's a fringe position. Interesting topic. So the structural account instead requires a relation of structural isomorphism between M and T. But again, right, what makes M represent T without T representing M? Shouldn't be a not there, breaks the symmetry. Well, people like Bueno, who are advocates of the structural view, say representation is an intentional act, relating to objects, intentionality again. And then there's the inferential view, which I quite like, because the inferential view is quite metaphysically open-minded, one might say. And that always strikes me as quite wise, because I think our ability to do metaphysics is very limited at best. So on this view, A represents B only if the representational force of A points towards B. Representational force, again, is something like aboutness or intentionality, here called by another name, and it allows competent and informed agents to draw specific inferences regarding B. And the inferences involved, of course, will be set by the context, the interests of those involved, who will be scientists, presumably. Okay, so representational force, the appeal to that breaks the symmetry, not breaks the asymmetry. My word, I got up early and didn't check my slides properly. Oh me miserum. Okay, so in summary, all of these accounts of representation involve aboutness and something else. And it's the aboutness component, or the intentionality, that provides the directionality. And the simple move in what follows is, oh, let's just cut that out, right? Cut out that crap. That's what makes people doubt that these systems contain representations, because they're worried about the aboutness. Okay, so let's assume that AIs can't independently form internal scientific representations. Of course, they might form entities that would be scientific representations, were they to involve the appropriate aboutness, relation, intentionality. So we could define quasi-representations in a subtractive way as representation minus aboutness relations. Very elementary, simple idea. So if you prefer a similarity-based account of scientific representation, for example, you would think that X quasi-represents Y when X is similar to Y. And of course, the advantage of using the notion of quasi-representation is it doesn't make a choice between the existing accounts of scientific representation. It's nicely fits with all of them. And I haven't mentioned mental representations at all here. I've avoided any discourse about those. There is a refinement I think is necessary, however, which is that we want to allow for scientific misrepresentation. And this has actually been a problem for similarity-based and structuralist accounts, right? You know, if there's always that similarity there between the two things, how could they ever go wrong, right? And but there are scientific misrepresentations. So Suarez's account is perhaps one of the most effective ways, or one of the nimblest ways at least, of avoiding this issue, because it only involves drawing specific inferences, right? It doesn't ascribe validity to the inferences that are drawn or any surrogate like that. They could be inferences that lead you to false, even, you know, catastrophically false conclusions. So I think let's instead define quasi-representation. Let's be more careful as what's present when aboutness is subtracted from a representation that is not also a misrepresentation. There you go. We have our refined definition of quasi-representation. Okay, so I think cases of natural meaning, as Grice called them, are good illustrations of the idea behind quasi-representation. Give dendrochronology, consider tree rings. Let's grant that these are not representations of how long trees have lived in the past or of climate conditions in temperate regions. Well, they aren't scientific models either. However, pretty obviously, pretty clearly, they are the basis for generating representations of these things by human interaction. On an inferentialist view, you know, it's almost like you've just got to spot the tree and then appreciate the causal connection between some features of that, of those tree rings, or of the severed stump. Could be a log from the tree. You just got to appreciate those connections between various things in the world. You appreciate the causal connections that exist, then it becomes an inference tool for you. So then it becomes a scientific model. Why not? So of course, there are many inferences you can make from them, more than first meet the eye, actually. It's quite interesting. The scars from forest fires are quite fun. And it seems it's really uncontroversial, right, that these are quasi-representations as defined. No one doubts that. But there might be some kind of really philosophical, you know, hair pulling and agonizing about when is it, how exactly does it become a representation? And my kind of feeling about this is that it really matters very little for practice. And, you know, yeah, if you want to have that debate as a philosopher, great. But I kind of rather try to talk to scientists a bit more and like draw some conclusions about doing actual XAI. So the new improved AI-specific NMA is going to have quasi-representation instead playing a central role. Notice now we don't need any mention of accuracy either. So it's quite neat. And actually, of course, because the presence of a representation that's successful, it implies, or presence of an accurate representation, I should say, implies the existence of a quasi-representation. It turns out here that this argument is, strictly speaking, better in various respects, right? Because of, you know, results about conjunctions and probabilities, which I bother to go through. Kind of obvious. Okay, so let's finish with a quick case study. I mentioned GraphCast, super cool. GraphCast is a weather prediction deep learning model created by Google DeepMind. And basically, it takes grids over the Earth, 0.25 degree longitude, latitude grids, and it takes a lot of variable information in those grids. It takes wind direction and U and Y wind direction. So two components of wind direction at a variety of pressure levels. Pressure levels really correspond to heights here. So it takes this information at various heights. It takes temperature, it takes humidity at surface level and various heights, and it crunches it. And it's fed on data of this kind. Actually, the reason it considers grids like this is because that's the nature of the data. So it comes straight across from the data. It considers like 30 to 40 odd years of data of this kind. And then it crunches it, it connects it in a graphical format. I think the main point of the graphical connection, eponymously, okay, it's GraphCast, it's a graphical neural network. The main point of that connection process, I think, is to allow relations of influence that are distant. Right? So one way you could think about doing this problem is consider a square and then only consider the effects of changes in all the other squares that are proximal to that square, and then try to iterate like that. But that isn't what this does. Okay, it can consider how a difference a long way away might affect how something near changes. So it's really interconnected, I guess is the way to describe it. Okay. So it's super successful. So that was the point there. Just crucially, it considers allows the model to consider different causal distances. Might put it that way. And also, I mentioned earlier briefly, it has no physics programmed in, right? So the best deterministic alternative is a supercomputer that had loads of physics programmed in over many years. And that system is not as good in various respects, right? So GraphCast is about 10 times faster while using less computational power. It actually turns out that when it comes to things like tracking cyclones, it can actually be better as well. And interestingly, it can be even better still if you cut out some of the older data. If you train it on data that's a bit closer to now, it gets a bit better, which perhaps suggests some change in global conditions that isn't reflected by the variables in the model. Wonder what that could be. I won't be a climate change denier. Okay. So here we might get a brief video of it in action if we're lucky. It might play, it might not. The main reason I wanted to play this was just to show you that it's quite remarkable how much it looks like fluid flow, even superficially. But it doesn't want to play. It's not playing today. Maybe there's no internet connection. Okay, so are there quasi-representations inside something like GraphCast, and what form do they take if so? Now, this is very interesting. As well as reading the paper on GraphCast, I've also watched various talks that have been published online about GraphCast by team members. And in some of their talks, but not in the article, it actually states specifically that they aim for the system to learn the approximate physical laws governing weather dynamics from real data, which is quite cool. But of course, we can also use what we know about the system and how it works, the architecture, the programming, etc., to help us in reasoning about this. So has it learned some approximate physical laws governing weather dynamics from real data? Well, the fact that we've got this complex graph involved in the network makes it quite plausible that GraphCast is not employing something like a toy model, like a highly idealized and extremely simple model. Actually, some authors have suggested that, that AIs do use these sometimes. In this case, certainly it seems very unlikely. The key idealization really is the coarse graining, which is present in the training data. Okay, and then there's just the variables and how they change, a lot of variables. But look, I mean, beyond that, it does seem pretty plausible that GraphCast latches onto causal patterns that are reflected in its training data. So for example, you know, we know independently a lot about how cyclones form. We know that global warming is problematic for one reason, because it increases sea temperature, and that's responsible for driving more cyclones, right? Actually, what you want is you want the wind to be relatively still at lots of levels, and then you've got enough time for it to build up. If you have considerable difference in wind velocity at different levels, different pressure levels, then it's harder for it to build up, right? So we know that, and we can look at those kinds of cases, and we can see that it makes brilliant predictions, better than we can by hand. It's like, could it do that without latching onto some causal patterns. You're back to some kind of intuition here, but the intuition here seems much stronger than the traditional NMA to me, right? I've just got to latch onto some causal pattern. That's all. Didn't ascribe any semantic properties to it. Okay, so when we think about XAI here, we think about, can we get this out and can we get cache value from it? Now, of course, on an inferentialist view, if you can just get something out you can make useful scientific inferences with, then you've got something like a scientific model or representation. And it does seem from this kind of argument that you've got some reason to think something like that's inside. But I think it's quite plausible that if there is, I mean, imagine there's just something like a single law in there. I think we would want to call it, actually, we can call it a quasi-law, like a quasi-representation, as I have, I think in the paper here I'm working, I've worked on this topic, I call them quasi-laws. But I think that the lesson here would be XAI would probably involve trying to move backwards, right? So often in the history of science, we started off with relatively simple and highly idealized models, and then we built things in, right? So you start with a simple pendulum, then you build in friction. For example, you build in forced motion. You build in motion in 3 dimensions, those kinds of things. You add complexity. Here, it looks like perhaps we'd want to try to subtract the complexity to get something out that has the kinds of theoretical virtues that human beings will value. Actually, I think this also is not surprising in the context of other work that's happened in AI in science, like the Eureka, for example, which got some of the remarkable results about double pendulum motion. There you end up with something very complex, and what they actually did was they tried to derive or work backwards to get the simple pendulum. Okay, actually, they tried to get the AI system, program the AI system itself to be able to work backwards, which you can do, right? There are processes that you can use to do that. Work on areas like symbolic regression has really come on a great deal in recent times. Okay, so that is the end of the paper. Thank you very much for listening. The original paper that I talked about is available in Synthase and it's open access. And the other paper is under review. And if you are the reviewer, I trust you will accept. Thanks very much.
No, well, thank you very much for your talk. Yeah, so I agree with what you said here, and and also I'm interested in the last part of your talk that I think the main part of the problem here is that, well, yeah, machines seems to have a representation, and I do agree with you that this representation has a certain semantic relationship with that external nature, the world. I agree with that. But the problem is that what this representation really is, we don't know the representation of the machines. And so I agree with you that XAI here is important. But XAI is a kind of IBE by itself, right? Because the machine's representation is very high dimensional, and we project it in a very low dimensional space. And from this, well, the projection on the low dimensional space, we make an inference that the machine's representation is such and such. But this is an IBE, inference to the best explanation again. So it seems like that there are two inference to two IBEs here. One is a IBE from machine representation to the reality. And the second is IBE from the XAI's lower dimension data to higher dimensional machine representations. So I was wondering whether these kind of double use of IBE affect the nominal problem.
Yeah, so for present purposes, I do want to avoid the talk about representations in the machine. If I do happen to believe they're there, but for this argument, you don't have to. So, I mean, maybe if you think about it in an inferentialist way, it becomes more plausible, right? So you could do XAI in different ways. I mean, you could not try to find out very much about what the system is actually doing, and you could do XAI in a different way. You could try to instead generate a story that you could work out what the algorithm is. It's instantiated by the system, and then you could, even maybe in some limited number of cases, then you can generate some model that saves those relationships. So maybe it's a how possible, some people would call it a how possibly model or something like that. Personally, I would think that could be a scientific explanation, but some people require truth or approximate truth in the explanation. So you could do that instead, but at least this has the force, hopefully, and we don't know if we'll be successful, of encouraging people, if you do look at what the system's actually doing, you can probably find something that's useful, right? That's the push. It may not be that strong a push, but it's a push to really do that. And no, I don't have the answer as to. I mean, it really does depend, right? It depends on how much you know about the architecture of the system and how that works, as to what you can find out by playing around with the system. If you've got like a convolutional neural network, you can have a pretty good idea that which pixels are being, or which shapes can be picked up at various parts of the layers, right? As you go further along, they're going to be more complex shapes. We know that kind of stuff, and that will then help us, I think, when we're probing the system, when we're doing things like ablation studies and whatever. Another thing we can do, of course, is just look at how the AI works for some specific set of inputs and some specific set of outputs. Not consider, so in the case of AlphaFold 2, you could just look at particular kinds of proteins with similarity relations. In the case of GraphCast, you could just look at cyclones, maybe, right? And then you could maybe get some inkling about, if you're lucky, about maybe not the full quasi-law that it instantiates, but some consequence of that, right? Something that is derivable from it. So, yeah, I think this is, I mean, it may even be where you may even find there are different, I mean, some of the great experiments, so I'm rambling on a lot, but I just want to tell you about this. It's really interesting. Some of the most interesting studies, I think, nowadays even suggest that you can do physics with different concepts, right? Starting off with different variables and get the same results. Pretty remarkable studies that I've been reading recently suggesting this. So I don't know if I answered your question. I rambled.
Well, yeah. So I think my point is that so the real problem now is that machines seems to have a very accurate representation of the world, maybe more accurate than what we have, but we don't know what kind of representation it is. So even if we apply numerical argument here, the problem is that, okay, so seems like the machines have a representation all, and that because of that they have successful prediction. So by applying the numerical argument, we can believe that all is true or quasi true. But if we do not know what all is, then the argument looks like a Morel's virtuous diva. So this pair works because it had this sweeping pair works because it has sweeping power or something like that.
I mean, lots of things can have causal relations to other things, right? So that, I mean, in a way that might be, let's not talk about representations, let's talk about causal relations. Lots of things can have causal relations to other things. And once we appreciate something about, once we grasp something about what the causal relations are with our own concepts, we can draw useful inferences from that. So I do think we can impose some of our own concepts in some of these cases and get something of value. It won't be the whole of what the system does. We're probably never going to appreciate the whole quasi-law. I mean, in something like GraphCast, let's say it's really there. Maybe we'll never get that. That doesn't mean that we can't chip away and we can't get some parts of that, some consequences of that, some components of that under a particular conceptual interpretation. I mean, sometimes you can express the same thing, you can use the same concept to describe the same thing somewhat differently, right? I mean, you can have energy representations and force representations, for example, in physics. You can have Lagrangians rather than or you can have Hamiltonians. So yeah, I mean, it's quite possible the system's using more advanced stuff than we can than we have the conceptual apparatus to replicate. That's true. That's true. But I wouldn't despair of finding anything of causal value, inferential value, right? For example, because of the causal connections. The devil's always in the detail with these cases as well, I mean, yeah.
I think my question is a follow-up to the exchange you just had. So if so, just take it as an invitation to say more. I was wondering if I'm not Suarez about models, why I would infer from the fact that I think at some point you used the phrase inference ticket, that this model, sorry, that I have an inference ticket here. And we have a story about why it's a good inference ticket, to the fact that we have some kind of quasi representation. So could you actually get sort of all of the conclusions that you want without invoking this notion of representation and just saying, look, I have a story about how these things are acting as good inference tickets.
Yeah,
and I can-
absolutely. So the way I see it is that so one possible account of quasi-representations is as inference tickets. Another one is as similarity relations. Another one is as relations of structural isomorphism. There may be others. So it's just saying whatever you think makes scientific representations work, let's just take that thing and cut out the aboutness, cut out the intentionality. Whatever's left. I mean, actually, personally, at least, I think you could have similarity relations. You could have relations of structural isomorphism. You definitely have inference tickets, and of course, the inference tickets account kind of does cover the other two, because it could be in virtue of there being a structural isomorphism, for example, that you are able to make good inferences that you want to make. Yeah, personally, I mean, I like the inferentialist view, as I said, because I think that it's and I would be happy personally just discuss the way I would personally think about it, not necessarily so much in a paper, would be think about, can we get anything out that has a causal relationship that we can make useful inferences from? I think that's fine, but I want to invite those who disagree about scientific representations to also believe in believe that this argument is at least as good as the traditional NMA one. I want to invite them to believe that too. So if I can, that's nice.
Yeah. No, that's helpful. I think what I would then want to push on is something that you said in the answer, which is like, well, these other accounts of models give us a nice account of when and why we have a good inference ticket. But at least for me, I've always been a bit mystified by Suarez, like how it allows in misrepresentation, but in a way, you need a background account of what counts as a good inference in light, or why this system ends up as a good inference ticket.
Mhm.
So it just
yeah. So I think that you could argue that it's a metaphysically incomplete account. But I would say that most of the best metaphysical suggestions they're found in the other accounts. So I'm not saying that I tend to be a bit more ecumenical about this, right? So I think that you could probably find cases where you probably can find cases where the fact that it's a valid or a useful inference ticket, that's caused by either similarity or structural isomorphism. So I suspect there will actually be a list of different features, and it may actually depend on, also, it's going to really get complicated. One of the things philosophers do a lot, they really oversimplify too much. It's probably going to get super complicated. It will depend on the kind of inference you're making and the context, actually, what the driving factor will be, I suspect. All I would say is that I think that there are clear cases like the tree ring case where you spot something and you know that there's a particular kind of causal relation between phenomena, and that gives you the ability to infer. And I think that we should reasonably believe that there are causal relations of that kind between target systems of deep learning models and what goes on inside them.
Yeah, thank you for the interesting talk. Basically, I have similar questions with Kate, and so my question is about the causal representation's power to do what you want to do, right? So if the causal representation is the representation minus some agential power or the semantic or intentionality, something like that, then if we set aside the inferential conception of representation, that it can reduce to structuralism or the similarity-based view, right? But it's well known that the similarity is too weak, right? So I have two solid objects, and we don't want to think that this causal represent this one, even if there's some similarity between the two objects, right? So
of course, there's some similarity between the features in the real world and some feature representation in the neural network. It doesn't follow that it represent or the causal represent the real features of the
Sure,
system. So I wonder whether the causal representations can do the job instead
Sure,
of
I agree. So, but I think that difference is a difference on views of what the thing you should add to the aboutness is. So I think it's right that, I mean, I think the similarity-based account is the weakest and the least plausible of all of them by quite a long chalk. Partly because in order to deal with objections like the one that you've made, people need to add more and more and more to it. I mean, even going back to like Hesse's work, of course, we have the positive analogy, the neutral analogy, and the negative analogy. Those kinds of ideas are invoked normally when we're using analogies in science. And normally when we're thinking about similarities, often we're going to be using argument from analogy. You can use argument from homology too in some cases, but yeah, I think that's right. So I think that your example is fine. Of course, in some cases, similarity is not going to be enough to drive, I agree, scientific representation. But would you say in all cases, it's not enough? I don't know. I mean, there are so many different approaches, contexts, ideas in science. I mean, it's messy. So I'm always, a bit nervous about generalizing because so many times I found that different scientists do things in different ways. So I think maybe sometimes if the problem you're concerned with, if what interests you is appropriately fixed, then maybe a similarity relation could be enough to give you an inference ticket. Yeah, I think so. Sometimes, even if not always. And your worry is that there are lots of different kind of similarities. But if you're interested in one particular kind of thing, a lot of the similarities you won't consider.
Yeah, actually, I suppose that the semantic considerations might be required in some way.
I mean, in the case of what I've argued here today, anyway, I've been talking about causal connections between what the model does and the world, which are not the problem with a lot of similarity relations is they're not causal, right? But you can have legitimate scientific models that are not based off causal connections. Why not? I mean, it just depends on what you're using the model for, what the case is. But yeah, a lot of the most valuable and important ones rely on spotting those causal connections. And those are the kind that I think are important in this case.
Yeah, I have a simple question. Okay, just a very, very simple
I
question.
probably don't have a simple answer.
When people are skeptical about whether AI have representations or even quasi-representations, I could see that happening with like maybe ChatGPT. People play chess against it and they wonder, does it really have a model of a chessboard? Or
No.
yeah, maybe not. But your example of GraphCast is literally producing a graph. So like, why doesn't that just make people just say, look, here's like a picture of the Earth and its temperature and stuff like that? Why isn't that automatic? Why wouldn't that just convince a person that it has a model of, the weather on Earth?
Why wouldn't it? Or
yeah, why wouldn't it? I mean, why? I
don't know. I'm not a skeptic. You'll have to ask. So I mean, I think also this case is interesting because these are all. I mean, the data here. It's not about. It's not about theoretical entities as such. Just like wind measurements, temperature measurements, humidity. It's pretty in a way that the data that goes in is of a pretty mundane kind at each measurement point. It's not. It's not extremely hard to measure, and it doesn't posit bizarre theoretical entries. There are kind of macroscopic variables involved. So yeah, it seems really hard to imagine how it would. I mean, the way it works is you put the initial data you put in is all those variables 6 hours before and now, and then it generates +6, and then you feed back in now and the +6, and then it gives +12, and you put in the +12 and the +6, and it gives +18 hours, and so on, up to about 10 days. Yeah, it seems really hard to imagine it would work without some kind of effective representation of causal relationships between those variables in different places. It just seems very difficult to understand how it would be so damn good. I mean, even better than the supercomputer which has the physics programmed in some cases. Yeah. And the really interesting feat, I mean, and I think it's actually, maybe it's evidence as well. It's evidence that it does well, perhaps, that when you train it on when you train it just on that data that involves like the last 20 years rather than the last, say, 35, it actually gets better on cyclones, right? So that suggests that there are other variables that aren't in the model that are significant to the laws that obtain. Which seems very plausible. These are phenomenological laws, right? Not fundamental laws. Thanks very much, John.
Thanks. Yeah, thanks for inviting me, Frank and other organizers. I'm coming from the Seoul University. I'm currently working in the Department of Science Studies, and I'm directing the Center of the AI LC. So today I want to talk about the algorithmic transparency. So this is how I proceed. So first of all, I introduce why it matters, and I introduce different approaches to algorithmic transparency. So roles distinction, value-based framework, and then I propose new approach to the transparency by asking transparency of what is opaque, what is transparent. So let's start. Actually, it's widely agreed that the algorithmic transparency is really important in the AI ethics. So according to well-known meta-analysis done by the Jobin and the colleagues, we can find 11 overarching ethical values and principles, including transparency, justice, and so on and so forth. This is table. So they surveyed 84 document, which include the software, not the hardware. And as you can see, the 73 out of the 84 cite the transparency principle as one of the major principles of AI ethics. And then justice and fairness, non-maleficency, responsibility are quite frequently cited ethical principles in AI ethics. And here you can see some relationship between transparency, explainability, understandability, and so on and so forth. And this is some pictorial overview of the principled AI drawn by the Buckman Climate Center at Harvard University. Here, the transparency is among the key theme. Here, you can see this one. Yeah. So there's a section for the transparency and explainability. So, in a sense, transparency has well-established meaning and usage in the political philosophy and political sciences. Even though there's some controversies, disagreement among the scholars. So basically, it means that disclosure of access to information, primarily of the government or the public institution to civil society. So it's believed that such transparency is crucial to maintaining the democratic society. So before we proceed, there's some caution note here. So we are not calling for the unlimited degree of transparency, because there might be tension between different forms of transparency, or the transparency principle might be in conflict with other ethical values, right? So you might say the sufficient level and appropriate forms of transparency matters. So why transparency matters? First, it's crucial for the holding government accountable, or you might say legitimate, right? So openness in governmental process allows citizens to monitor and evaluate actions of their political decision making, thereby reducing the likelihood of the corruptions and misuse of power. Second, we want to know how the public policy is and political decisions are made. So transparency enables citizens to make well-informed decision and allows citizens to participate in a democratic discourse. Third, when people have insight into the decision-making process, they are more likely to trust the system, even if they disagree with a specific outcome. So the accountability, informed decision participation, and enhancing trust are the ultimate goals of transparency in general sense. So applying this notion to AI, transparency in AI can be broadly construed as the disclosure or access to information on the design, use, operation, and other features of AI to those affected by this use and to the civil society in general. The problem is how to implement this idea, right? So one example implementing this broad idea is Stanford Index of the transparency. So in 2023, Stanford University Center for the Foundation Model introduced this index, transparency index, to quantitatively measure how transparent the foundation models are. So they analyzed 10 major models like Llama, GPT-4, Claude, or something like that, and finding the average scores of the 37 out of 100 in the 2023, and Llama got the high scores of the 54. And they highlighted the general lack of the transparency and hoped that the index will contribute to improve the transparency in the foundation models. And then the next year, 2024, they reported the updated score. And the mean score was the 58, with the highest one of 85. Yeah. Of the Hugging Face star coder, right? So huge increasement in the 1 year. So how they calculate the number, right? So they selected 100 indicators to calculate to sum up. So they divide into actually three parts, three 3Ds: upstream, model itself, and downstream. So upstream, those transparency of resources and procedures used in the training and validating models. The model domain relate to the information about the model itself. And downstream domain addresses the transparency related to the model's use and the distribution. And this is the whole list. And I'm not trying to engage in the detailed discussion of the weakness and the strengths of this index, but nevertheless, building on the criticism from the Alyssa AI, I try to point out some limitations of the index. So first of all, I think, and they claim that the index does not measure properly the transparency of the foundational models. So called the central to the transparency of the LLMs is whether or not the weight of the models and training data are available. So without these things, many of the claims made in the model report are unverifiable. Interesting thing is that GPT-4 received 5 score over the 6 without disclosing the internal weight of the models. So this severely underestimate the importance of model weight in the foundation models. Second, it doesn't clearly distinguish between the model itself and the commercial product based on it. So it overemphasizes the information related to the product, commercial services, rather than the model itself. So for example, the user permission is important, and models impact the society or market is important, but it's not directly related to the opacity or transparency model itself, right? So believe they fail to fully acknowledge the relevance of the explanation, understanding, and transparency. So given that the ultimate goals of transparency are accountability, well-informed decision-making, enhancing trust, it's very hard to achieve it without explanation, understanding of how it works. So, in this talk, I try to introduce a new comprehensive framework. But you might think that there are many good accounts of transparency in this literature, but I don't think that is the case. So I think there are several regions developed a new comprehensive framework for the algorithmic transparency. One of the reasons is that there are two streams of the literatures. One is about the explainability in XI. It's about the political philosophy of transparency. So I try to bring together to make a whole the comprehensive framework, right? So first, transparency is mere disclosure information, as discussed in the political philosophy. It's not all there is to the algorithmic transparency. So it is, yeah, fundamental aspect of transparency, but it does not fully capture the important dimensions of the deep neural network or the opaque algorithms. So we need to consider the inseparability from the explanation and understanding. Second, it should be able to respond some skepticism of the call for transparency or explicability principle. And third, the new classification system can help us to see what forms of transparency various XI methods are intended to improve, and indeed they do. And first of all, I thought that this inseparability from understanding explanations are widely acknowledged in some literature. For example, the Aslamaya principles talk about two forms of transparency, which are closely related to the explanation and understanding. And the other dimensions from the Nadella and IEEE, the transparency are closely related to the understanding and explain why, right? Second, I think new framework can help us to address some of the skepticism against transparency ideal or the explicability principle. So this is a well-known paper written by the Anani and Crawford, and they are claiming that the transparency ideal failed, and they listed 10 reasons why it fails. So transparency can be disconnected from power, can be harmful, can occlude, can create false binary, and so on and so forth. So we're not gonna discuss all the details, but the point is that seeing inside to see what's going on inside is not enough for understand or know what's going on and to get some insight over how to govern all the decision-making system. So I think we can agree with some criticism, but we suggest that we can redefine transparency as instrument, not as an ideal, and as incorporating understandability, not as disconnected from the understandability and explanation. So transparency must go beyond the mere visibility to incorporate elements that enable us to understand the decision-making system. So when transparency is redefined as instrument or tools for enhancing understanding, there's no reason to remain a skeptic. This is the response to the Anani and Crawford. And another skeptic is Robbins. So Robbins claimed that the demand for the algorithmic explainability led to a paradoxical situation where we do not need to use machine learning algorithm at all. Why is that? Because the principle of the explainability or the transparency requires some explanation of how the algorithm produced the given judgment. And in order to evaluate whether such an explanation is acceptable or justifiable, we need some criteria on which we judge the acceptability or justifiability, right? So if we already know this criteria, we don't need to build deep neural network system. We can use old-fashioned rule-based system, right? That's the idea. I think that this kind of criticism loses strength once we distinguish different forms of transparency. In the later, I will distinguish model transparency and distance transparency. So this is basic idea. So information on how the machine learning model works does not tell us directly how the particular outcome come about. And explanation of individual outcome might not be insufficient to understand how this making works in general. So the transparency model does not guarantee the transparency of decision and vice versa, right? So given this distinction, the call for the transparency is not call for the moratorium of the machine learning algorithm. Okay, so one lesson is that we need to distinguish different forms of transparency, right? So one inferential account and distinction is coming from the Yana Bottles, where she proposed 3 forms of opacity of algorithms, right? The first one is intentional opacity, second is illiterate, and third is fundamental or intrinsic opacity. So intentional opacity results from the company withholding the information. They intentionally hold that information without disclosing it, right? For some reasons, for some intellectual property or something like that. And machine learning algorithms can be opaque to some non-expert because they don't know how it works, right? Third one is fundamental. The fundamental opacity, unlike the previous ones, is caused by the intrinsic nature of the machine learning. So she said that this kind of opacity is mismatch between mathematical optimization in high-dimensionality character machine learning and semantic interpretation demanded for human intelligibility. So these distinctions are quite influential and the valuable contribution to this literature. But I think it has some limitations. The first one is that distinction is made by what makes system opaque, not what is opaque, right? So it remains unclear what is opaque. For example, the illiterate opacity is caused by the lack of knowledge of the non-expert, right? But it's unclear what the illiteracy makes opaque, what information is transparent to the illiterate expert. And second, the concept of intrinsic or fundamental opacity above is ambiguous in that it failed to distinguish 2 senses of what is transparent to what is opaque. So it might mean that algorithm is too complex to comprehend how it behaves, or it might mean that it's hard to know on what basis particular distances are made. So to illustrate this distinction, let's consider the two cases given by the Darrell himself. So first one is the algorithm for the classifying handwritten numbers. So it's kind of a number classifier. So she pointed out that even if we can see the weight of hidden layer between input and upper layers, we are not able to understand the algorithm. Why? That artificial network doesn't see the numbers as we humans do. We interpret the numbers in semantic ways, but we use some straight lines, curved lines, closure, and opening, something like that. They don't do that, right? Second example is spam filter. That spam filter makes use of the linear regression to categorize emails by weighing the numbers of a particular word contained in the emails. So she pointed out that the way spam filter classify email is different from the way we do. So we categorize emails depending on the semantic content of the word, but the spam filter classify by the weighing the number or frequency of the word, like the hour click in the middle of something like that, right? So I found her treatment of two cases problematic. First, in the case of the number classifier with the one hidden layer, is not usually considered the black box. So literate expert can tell the number classifier works, and even they can't predict the numbers of input images. So there's a sense in which the number classifier is somehow transparent. And second, all view the spam filter as opaque because they produced the outcome by weighing the word, not by the semantic content. However, there's another sense in which it can be transparent in the sense that the word on the which spam filter base is classification are interpretable to us. So we can understand why this spam filter classified this email into a spam because it uses this word, this uses this word, right? So we can understand why the spam filter classified this email and that email to a specific way. So the point is that there's a sense in which spam filter is opaque, but there's another sense in which it is transparent. It means that the fundamental opacity is not a monolithic concept. So I try to suggest that we need to distinguish the model of transparency and distant transparency later. Okay. So I try to suggest we have to ask what is transparent and what is opaque. Not what makes an algorithm opaque. So algorithm models can be opaque in the sense that it's difficult to understand how the model works and behavior because of its complexity, or in the sense that it's difficult to know on what basis the algorithm's decisions are made. So here's fundamental opacity conflate two forms of transparency. So these are what I call the model transparency and distant transparency. So let's ask what is opaque, what is transparent. But I found that there's two ways of asking what. So one is that what information about ML models is and should be transparent. Second one is what values the ML models do pursue or should pursue and realize. Those are the what questions, but quite different. So I call them the information first approach and the value-based framework. So information first approach only demand essential information necessary for accountability, informed decision, and trust. In contrast, the value-based approach demand information of justification and legitimacy. So they ask what values they pursue, whether they are legit, acceptable, and how successfully the value are realized in the system, right? They want the justification of the justifiable values in the system. So what I call the value-based approach, studied by these scholars, Laureate, colleagues, and Boosman. And Boosman try to explicate the concept of transparency in the following ways. So there's some overview of different values relevant to the system, and then conceptual specification of the values, and then quantification of specification into the design requirement, and the measure how successfully they implement the values, and the further illustration of the value conflicts, so on and so forth, right? So this perspective can be valuable for the external auditor and examiner who are interested in the ethical design, but I don't think is the proper way to see and ask the what is opaque, was transparent. Especially this approach raises some the practicality issue and feasibility issue. So on the value-based approach, it seems to me that transparency is assumed to be intrinsically valuable. But we maintain that transparency as instrumentally valuable to achieve other fundamental goals like accountability from decision and trust, right? So it's valuable, but if it doesn't contribute to the other fundamental goals, it does not have any real value. So the question we have to ask is what kind of information provision is instrumental to the achieve goals, rather than what values the model embody and how. Second problem is feasibility. So for the transparency to be meaningful, it must be visible and actionable within the context of the development and deployment of AI. So I suppose it's quite natural to reveal some pieces of information involved in the designing, building, and training, and validating, and using, exploiting the models, right? Value-based approach imposed additional burden to requires more the information, what values they pursue and do embody in the system. So I think it's too demanding. So it's not the case that developers are always aware of the values their models embody. And to specify what values and how it's embodied, the system's working requires additional burden. I'm not talking just about the amount of the burden. I think that might not be the right kind of burden that developers have to take, right? Second one is this, how can I say, even if they report, they can report this system embody this kind of values and how successfully, right? And we have to determine their report is trustworthy, their report is reliable. So to determine that their report of the value embodied in the system is true, reliable, then we need some information, right, about machine learning models. So the second problem for me. And the third one is about goals of transparency principle. So they take the literature of transparency in which they are engaged different from the XI and explainability literature. So they thought that they are dealing with somehow different thing from the XI and explainability. I don't think they should be distinct. They are not competing goals, right? They should be connected and integrated. So in sum, the value-based approach is less practical and actionable than information-first approach. So let's ask what is opaque, what is transparent. We suggest 4 different forms of transparency: use, data, model, and distant transparency. So how much time do I have? Okay, good. Yeah. Yeah. So I try to introduce 4 forms of transparency, and I try to compare our approach with the categories distinction of the levels of transparency. So, okay. First one is use transparency. Why? So algorithmic assisted decision-making system can be made more transparent by disclosing information about whether the algorithm is being used for some decision-making processes, for what purpose it was being created and used, and who has control and oversight on the algorithm. So the information about the presence and the goal and objective and the domains of application and relevant human involvement is crucial element of the use transparency of the machine learning system, right? So it reflects the basic fundamental sense of transparency as information disclosure, information provision, which is not different from the transparency in the other domains. So it's not driven by the black box nature of the machine learning algorithm. Second, data transparency is about the examination of training data and validation. So the examining the training and validation data is crucial to determining whether some utilization of machine learning algorithm is ethical or not. So we do not call for the ex-ante disclosure of all the data used in the training and validation. But there are some ways to enhance transparency of data by reporting the source, the processing, and the quality of data. So they can report where the data come from and how they process the data, and how good the data are, how they are a representative of the some population or not, right? So we cannot always demand the disclosure of data sources, processing method, quality to general public affected individuals. But when the ethical legal issues arise, then data should be available for the ex post transparency or external audit from the independent institution. So that's about the data transparency. And third one is model transparency, and fourth one is distant transparency. Both are about the models, which are considered opaque and black boxed. So one way to make transparent models is that the model is transparent to you if you can see how it works. So if you are familiar with some literature of understanding in epistemology and philosophy science, there's some distinction between the object understanding and understanding why, exploratory understanding. So that's a kind of understanding some way to the object understanding, understand how the system works. So the model can be made transparent by revealing information about what features, variables the model uses, how they are weighted, what assumption the model takes. And yeah, this basic idea. So earlier I pointed out that the bottles distinction falls to distinguish between two kinds of transparency about the models. So one is model transparency, and another is what I call the decision transparency. So this is another sense of the transparency of model. So there's a sense in which understand an algorithm is to understand the region or ground for the output. What we can decision or judgment made by the algorithm. So algorithm decision making is transparent if we know the region, we know the ground, we know the basis of the decision making, right? So is reflecting the assumption principles of failure transparency. If some system fails, we want to know what on what basis that system produced that particular outcome, right? Of course, after disambiguating the fundamental opacity into the two forms, the decision and model transparency, there's some important question, difficult question remains, but in this talk, I will skip that part. Right? That's the new comprehensive distinction to incorporate the two strains of the transparency literature. And for the rest of the talk, I'll try to compare our approach, our proposal with Kathy Cray's notion of algorithmic transparency. So in the quite influential paper on transparency of the complex computational system, she distinguished three levels of transparency: functional, structural, and one transparency. So she shows that the algorithmic transparency spanned multiple levels. So first of all, the functional transparency. So model is functionally transparent if we can see what rules it follows to transfer input to the output and what algorithm it runs. Basically, it reminds me of the David Moore's levels of the function, algorithm, and implementation, right? So it's the highest level of transparency, functional transparency. And then structural transparency is in the middle. It requires knowledge of the algorithmic processes from the input to output, not just the algorithm performed. So I suppose the functional transparency can be considered as high level of model transparency, and structural transparency can be considered as low level of model transparency. And then there's third sort of transparency, which is called raw transparency, which is the knowledge of program running a specific hardware with specific training data. So my concern, first concern is about her way of equating the knowledge of algorithm with the code. So she assumed that knowledge of how the algorithm is processed is the same as the knowledge of the code it is written in. But obviously it's not, right? So that's my first concern. So we might understand how the predictive model works but it doesn't mean that we can understand all the codes, right? Or vice versa. So it's not a good way to formulate the algorithm transparency in terms of the code. And second concern is about one transparency. The CREO proposed that one transparency as distinct category. So functional structure and run transparency. Run transparency is different from the previous ones. Why is that? Well, we are very curious about that part. We don't think that run transparency is the sui generis category of transparency. So we propose is properly understood as consequence of the other types of transparency, rather than as a separate category. So flaws in running a given algorithm can be revealed by direct statistical analysis of data itself, or indirectly by examining the model's behavior judgment. So the problems in the run transparency can be revealed by the data transparency or the model transparency or distant transparency. So the run transparency is not the independent category that we have to consider. Right? So one of the idea that we share with CREO is that a good classification of transparency should be able to illustrate exactly what the XI method are improving and are aiming for, right? So by doing so, we can evaluate some significance and strengths and limitation of various XI method. So CREO attempts to clarify different XI methods as improving different types of transparency. So some XI methods are improving the structural transparency, some are improving the algorithmic transparency, some are improving the run transparency, or some are lacking the run transparency, something like that, right? So in particular, she claims that the line method can give us functional transparency, and the maximal activation method improve the run transparency. So in the rest of the talk, I will argue that it's not the case. So line, quite useful and widespread methods to the linearly mapping of the complex behavior of the deep learning onto the simple space, right? So we have the black box models, and then generate point over some space around some region, and assign weight based on the distance to the children, the region children point, and train the linear regression models to the weighted data set. And then we can see some relationship between the variables in the linear fashion, right? This is the idea. So it's considered a post-hoc explanation for the output. So the line fits a linear function to the behavior predicting models in a local regions around the particular point, right? So it's widely used. And CREO said that RIME does not improve structural transparency or run transparency. Rather, it increases types of functional transparency. It provides access to decision space, more relevant to the token classification, right? And she also said that RIME does increase transparency. It provides visible access to the higher level features of decision-making process. So basically, she's saying that it improves the type of the functional transparency. Yeah, we do not agree on the matter. So First, it's not clear in what sense this provides explanation of the model or rules of the models. Right? The functional transparency defined by the CRIL is about the algorithm or the rules run by the computational system. But she admits that it's not about the whole algorithm, but the partial algorithm used to make a particular decision. The problem is that the linear function provided by line is not the genuine part of the actual algorithm models, right? It's kind of surrogate models for the data set, right? So it's kind of local approximation or surrogate model of data, not about the models. So we claim that method, line method, enhances decision transparency. So it presents us with the important features that contribute to particular decision made, which enables to infer the basis of regions behind the judgment, at least in the local domain. Right? Second one is maximal activation method. Oops, yeah. So you might be familiar with this kind of the deep dream pictures by the Google. So it's usually, not usually, but often used to visualize how the image classification algorithm work. So the method start with some image as input and randomly modified so that it get the high score for a particular item. And then the activation maximization method generates the image that score highly for the particular item. So interestingly, this method can be used to find some flow in the training data. So that's interesting example where the research found that the typical image of Dumbo. Can you see the Dumbo here? Yeah. Used to train the model mostly contained arm holding the Dumbo, right? So the system learns Dumbo is associated with the arms holding it. So the model learned to associate arm with Dumbo, right? And what kind of transparency the maximal activation method improve? She said that the visualization provided a transparent access to previous unknown features of training data. So it increased one transparency. We believe that she's right to point out that the interactions of data and program can lead to errors, which the active maximization method can be used to discover. But error detection is not specific to any particular execution or program. So it's not the proper case of run transparency. So instead, the maximal active maximization method analyzed the inner behavior of deep learning, deep image classification models by synthesizing meaningful preferred stimuli. So by revealing typical cases of a particular class, the method make it possible to understand how the model classify the inputs to different categories. So by providing higher level understanding of how the model categorizes the input, we claim it promotes model transparency rather than the run transparency. Okay, so I said that earlier. Okay, let me quickly conclude. So to sum, we introduced a comprehensive framework for understanding the algorithm transparency, addressing limitation in previous classification of bottles and the krill and others. So by focusing on what is transparency, what is opaque, we have identified 4 forms of transparency: use, data, model, and this is the transparency. So by using this kind of classification system, we can contribute ongoing effect to make AI system more accountable and trustworthy, right? So of course, there's a bunch of important jobs to be done, to be remained, right? So thank you for your attention. Okay.
Thank you very much. Well, thank you very much for coming. Thank you very much for staying during the last talk. And thanks so much for the organizer, Frank, and others for making this happen. It's been great. Pleasure to be here. So today, I think that I hope that my talk gonna be a kind of a nice continuation to the talks today. So Darrell talk about representation, and Hyundeuk talk about transparency. So I here talk about the representation and its implication on the philosophical theories and concepts. So the title sounds a little bit kind of the intimidating, the algebraic and geometrical aspects, but I try not to torture you with the technical detail. I skip many technical details and I just give you kind of the idea. So don't worry about that. Okay, so oh yeah. Oh, no worries. Okay, so what I want to discuss today is the series of concepts. So there are, in philosophy, there's kind of two main views about theories, two views about concept. One is what I call abstractionism, or what Hayes called Aristotelian abstractionism, which this is a very traditional old idea that concepts are formed by abstracting away the difference among particulars and extracting the commonalities. So, and it forms a certain kind of hierarchical structure that the humans are animals, animals are organisms, and so on. So this is one idea. The other idea is the famous, the Wittgensteinian idea of family resemblance, where the concepts are understood as a kind of clusters of similar items. So, you know, the family resemblance, prototype theory in cognitive science, and also Richard Boy's homeostatics property cluster theories and so on. So these are two ideas. And what I want to do today is that compare these philosophical theories with the representation learnings in machine learning. So it is known that it is discovered that people talk about the representation machines forms inside a deep neural networks. So the deep neural networks are basically a classifier for the approximation of certain functions. So if you input a certain kind of image like tree, well, it outputted a tree. This is a tree, and if it's a car, well, it is a car. And inside of this process is a certain kind of the formations of representations. And there are several studies, mathematical models of such representation, which try to, investigate the nature of representation using the vector space and manifolds and hierarchical, putting in the hierarchical structures on manifold or vector space, and using symmetry, group theoretic idea, and so on. So there are a bunch of mathematical theories about representation. And so, and the goal, one of the goal is that to kind of align these representation with ourselves. So as Hyundeuk talked about, the transparency is very important. We have to know what is happening inside the machines, and understanding or unpacking representation is one good way to understand what they are doing. So these are the studies in the machine learning. And what I want to do is to kind of how to say update or model philosophical theories or concept using some result in the machine learning literature or representation learning. So that's a kind of general idea of today's talk. And as we will see, the key idea here is functional constraints, that data are constrained by a certain function. Not every data is possible. Only certain kind of data are possible. And what we want to try is to understand this kind of constraints, as a functional constraint, I would say, on data. And the good theory of concept, the kind of, how to say, the good theory of concept must take into account this functional constraints. And this function, the idea of functional constraints date back to the neo-Kantian, neo-Kantian like Hermann Lotzer and Ernst Cassirer and so on. So I want to connect these ideas with the machine learning theory. And by doing so, I want to update abstractionism and to model it in terms of conceptual lattice. And also this updates similarity view with the idea of representation manifold. So these are first goal. And the second goal then is that we end up with a kind of two different views on concept. How the question, natural questions is how do they get integrated to each other? So how to combine algebraic and geometrical aspect of G's concept. Oh, sorry, I forgot to say that the conceptual lattice is an algebraic structure. It's an algebra. It's a kind of, Boolean algebra is a type of lattice algebra. So it is an algebraic concept. Whereas manifold is a very geometrical concept. It's a geometrical structure. So the question is how to combine these two aspects. That's the last part of this talk. Okay, so this is a table of the contents. So first, I'm going to talk about the abstractionism and algebraic aspect of concept, and then the similarity space, and that is the geometric aspect of concept, and then ask how to combine these two aspects. Okay, so let me start with the algebraic side, the Boolean abstractionism and the conceptual lattice. So, as I said, abstractionism is a very traditional idea dating back to Aristotle, where conceptualization is a kind of predication, that is, that human is an animal is a predication, and by doing so, we kind of include human in the concept of animal, and by doing so, we kind of abstract the difference, a concrete difference among ourselves. So you are human being, I'm human being, and by saying so, we forget about the difference between us, right? So concepts are formed by abstraction in this way, and this is a kind of what is called either relationship. The human is an animal is an organism, and it leads to a certain kind of tree-like structure, hierarchical structure like this. So these people are human and host and other things are animal and so on. You see the idea. And either relationship here is a partial order because it is reflexive. Human is a human and it's transitive. If human is an animal and the animal is an organism, then human is an organism. So it is transitive. And so this gives a partial order. So the order that satisfies these, the relationship that satisfy these two actions are called partial order. And not just a partial order, it is also a lattice. And then what is lattice? Lattice has two algebraic operations, join and meet. Join here it gives a kind of least abstract concept of two concepts. For example, consider octopus and horse. And find the least abstract concept that comprises these two concepts, well, that it would be an animal, maybe, well, maybe different, but the animal definitely is comprised these two things. So this is a kind of the join operator. And the meet operator is the kind of opposite. If you have two abstract concepts, you find the most abstract instance of the two concepts. So what is the, the meat of the animal and the rational? What is an organism that is animal and also rational? Well, that is human. That is what Aristotle said. I don't know whether human is a rational being. This idea has been very much challenged these days. But anyway, that Aristotle thought in that way. So these are joins and meet operation. And this is defined for every pair. So for example, if you join the plants and the animal, you get the organism. And and if you continue this, well, maybe you might find the most abstract object that might be the kind of being or something like that. And likewise, you can go down by taking meat of things like horse and human and it's centaur or something like that. And if you go down to the bottom, well, maybe there's nothing that shares the property of plants and the organism, octopus and centaur and so on. So then it's nothing. But anyway, so this has the top and the bottom, and this gives an algebraic structure called lattice. The important thing is that lattice is a partial order that has joins and meet. All right. Then let me ask you questions. Okay, so this is a definition, but how to find a lattice? How to get the lattice? There is an algorithm for, well, there are algorithms that construct a conceptual lattice from data. And this is a very simple algorithm, actually, a very old one. So the data are very simple as well. So what you need is just a table, like an Excel table. On the column you have, on the rows, rows are individuals. A, B, C, D are the individual data, each individual data point. And on the column is a predicate or properties. And you check if that particular object, like this object A, works, and then you give a check, and it has a long, it has a check, and so on. So this is a very simple, kind of very maybe simplistic data. You can never think. So, and if you have this kind of object type, object property table, you can create a lattice. In this way, I don't go to the detail of how to actually create a lattice in this way. But the idea is you group those items that share the properties. So that means that there's a kind of if there is a matching pattern of check, these patterns leads to one item in the lattice. So, and the second, you see the patterns C, D, E shares these three properties, and then it creates a one item in the lattice, one node in the lattice. And what we are doing in this way is actually looking for necessary and sufficient conditions. So the matching the matching pattern actually suggests that they share a particular set of necessary and sufficient condition. So by finding these the items that that share certain necessary and sufficient condition, you can create a node of a lattice, and then thereby you are creating a lattice. So yeah, this is an algorithm, and this is called formal concept analysis. It's a very old technique, not really a kind of deep learning or anything like that. It's a very old one. But anyway, so there is an algorithm for constructing a lattice. And if you see it, well, you see a certain kind of pattern here. So that is maybe C is bat, and D, E is a bird, and so on. So you can name each node. Okay, sorry. All right. So that's a kind of the technical issue about constructing lattice and what's the philosophical upshot about it. The one thing that the conceptual lattice tells us is that not every concept is possible. So if you look at the conceptual lattice, there are connections, but not every node are connected, right? So if you look at this lattice, there is not connection between this and so on. So not every combination of A and B and C and D appear here. Just only subset of combination appear here. And that means that not every concept is possible. So Hermann Lotze made a criticism. Well, he's like a very old, 2 centuries ago. He made a criticism against abstractionism, saying that, well, you cannot create a concept willy-nilly. So for example, this is his example. Suppose you have a concept of chili and you have a concept of raw meat. Can you combine these 2 concepts and create a red juicy food or something like that? He said, oh, it's impossible. Well, it's ridiculous. But why isn't it ridiculous? Well, because there is no necessary and sufficient condition that picks just cherry and raw meat. If you want to create a red juicy food, you have to include all other stuff like octopus and apples and tomatoes and so on. So this is his criticism, but FCA, conceptual lattice, takes into account this criticism by restricting the bona fide condition to those who have necessary and sufficient conditions. So this is a good thing. And so from the conceptual lattice perspective, not every object property combination is possible, means that data table is sparse. So not every entry, there are certain patterns in the table and certain items are missing. So this sparsity leads to the Lotze's point that not every concept is possible. And this sparsity, we assume, reflect the certain kind of constraints in the way data are generated. So this is what I call functional constraints. So I want to take a closer look at this constraint. So, well, consider a set of properties and then consider its power set. The power set is a Boolean algebra. So this Boolean algebra is a kind of specific type of lattice, but it contains every possible combination of properties. So here we have properties X, Y, Z, and this is a Boolean lattice, Boolean algebra of X, Y, Z. So it has every combination of properties. But the point is that only a certain part of it is realizable. And how to express this idea? Consider function from this power set, property power set, to 0, 1 lattice. So there's the 2 lattice. So the lattice that have just 2 objects, bottom and top. And consider this function. Well, this function must be lattice homomorphism, but you can forget about homomorphism part. But this specifies which combinations are possible. So it says so if particular combination is possible, it gives 1 to that combination. If other combination is impossible, it gives 0 to that combination. So in this picture, it assigns 0 to the upper part and 1 to the lower right-hand side. That means that these parts are possible combination and these parts are impossible combination. And what is modeled in this very simple homomorphism is that, well, this W represents certain kind of word. So it is in the actual world, this particular combination is possible, and if this world, this is not possible, and something like that. And given this function, if you have an inverse image, then well, it gives it is a kind of a realizable concept in this world. So the blue part is a realizable concept. So you can think the possibility in this way as lattice homomorphism, and then we can think that conceptual lattice aims to capture this sublattice, that is this blue part. So this is what FCA or conceptual lattice is trying to capture. So that is, it is trying to capture the functional constraint represented as a lattice homomorphism to the Boolean lattice to 0, 1 lattice. Is that okay? Okay, well, I don't know. And so okay, so what's the point of thinking about functional constraint? Well, the great thing about thinking about constraints is it allows for inferences. And it allows for material inference. So this is there is a logic called attribute logic. This is a logic that you can do with a lattice. So the question is something like that. So in the attribute logic, you ask the question like this: of if certain particular item has a property P1 to Pi, does it also have other property like Q1 to Qj or something like that? And I think we do this kind of inference, right? For example, suppose you know that, well, you get the information that certain animal that's an echolocation. And also suppose that you know that that animal also fly. Then you can guess that, okay, so then that animal lives in a cave. Why is that? Well, because that's gonna be bat, right? But if you know that it's echolocates and it also swims, then it's gonna be maybe whale or some mammalian ocean living animal. So then you can guess that it is large. Well, obviously this is very kind of simple, too simplistic idea, but I think we do these kind of inference in everyday situations. And in the lattice terminology, this amounts to taking closure in the concept of, well, you don't have to you can forget about what is closure here, but anyway, there's a condition that this kind of inference is allowed. So you can make an inference from P to Q if Q is the included in the closure of P. So the closure operator allows for this kind of inference. And this kind of inference is called material inference. Material inference is the inference that you do by extracting the information and concept, not a logical inference, but you have to know what the thing is. This is not made possible by just a formal property of sentence or formal property or proposition, but it is it exploits the information in the concept. And the conceptual lattice kind of model this kind of material inference using concepts. Okay, so and this kind of material inference is made possible because that there are functional constraints. Because there are constraints on property combinations. That it's in this case, the crucial part is that there is no animal that have echolocation, fly, and non-cave living. So I'm not creating the truth of this sentence, but if that kind of inference is possible, that would be because there is no animal instancing all these properties. So the crucial part again is that there's functional constraint, and that means that conceptual lattice is not Boolean. So that's a point. Okay, so so far what I showed is that the conceptual, the abstractionism can be modeled with conceptual lattice, and the conceptual lattice reflect the functional constraint data, and functional constraint allows for material inference. And well, so far I didn't talk anything about machine learning. So and this is, I think, the slide that is slightly relevant to machine learning. So if you think the conceptual, the material inference in this way, this looks like the very simple form of natural language processing. So, well, this is a very simple, very old type of natural language processing. There's no attention or memory structure and so on. This is a very old one, so nothing comparable to LLM or ChatGPT and so on. But in a very simple form, the language model is, the goal of language model is to predict next word. And in the very simple model, sentence is modeled as a kind of backward word. It's a kind of multi-set or set. And predict the next word from the previous word, previous word with this. So it kind of estimate this probability function, right? Given that apple and is, well, it gives a high probability density or high probability mass to the word red and so on. And if you think in this way, the NLP algorithm is learning the constraints on word combination in terms of probability functions, right? So sentence one has an apple and red and so on. Sentence two has a big and a horse and so on. So all sentences are considered kind of the bag of words, all right? And exploit this information to predict the next word. And now go back to material inference in the NLP. As I said, in the NLP, object is a bag of properties. So it's just, the object here is expressed as the check mark in the property table. So this is a bag of properties. And what material inference does is that to predict other properties from observed properties. So that what it does is estimate this function. And this expresses the constraint on the property combination, it expresses constraint on property combinations as a lattice. So if you think about it this way, there's a certain kind of connection between the material inference using concept lattice and natural language processing. All right. So there are similarities. So inference of word and the properties, and that co-occur with a given words and properties. So they share the same kind of goal. And this inference is made possible thanks to constraints in the word and the property patterns or uniformity of nature, as a human would say. But of course, there are dissimilarities as well. Well, the first dissimilarity is that in the FCA or conceptual lattice, well, it represents constraint as a Boolean homomorphism or lattice homomorphism 0-1 functions, whereas in natural language processing, we use a probability distribution. And also, I think the biggest difference is that in FCA, we assumed that properties are there. So we assume the data table, but that is a future must be given. But in NLP, the algorithm learn the futures from data. So this is a big difference. And that leads us to the need for representation learning. So so given that this dissimilarity, the next question is how to learn properties or features from data. So that leads us to representation learning. And that's what I want to turn to now. Okay. So the second idea but concept is a similarity view. And as I said, that the idea is a concept is a cluster of similar items. So we switch the gear here. We change the gear. And Yeah, so the underlying idea is that, well, the concept do not have the specific kind of set of necessary and sufficient condition. That was the kind of Wittgenstein's point. You cannot give a necessary and sufficient condition for concepts. And rather they are kind of related to each other by family resemblance or homeostatic property cluster. And or membership is determined by the distance from the prototype and so on. So yeah, that is kind of the basic idea, but they usually assume that, so they talk about the similarities, and the similarity is a kind of distance. It's a kind of, well, anti-distance, but the kind of distance. That means that they assume certain kind of space, but it seems like that they have a very simple idea of what this space is. Or they usually assume the Euclidean space. But anyway, so that's the idea. And this idea is very close to the current machine learning framework. So we represent words and object in the latent space, which forms a vector space. But the latent space in the machine learning or deep neural networks is not Euclidean at all. But they are more complex. They have more kind of complex metrics, and they have non-zero curvatures. And the question is how the representations are distributed or clustered and so on in this latent space is one interesting area of research. So I'm going to turn to this area. And these kind of popular hypothesis among the machine learning literature called manifold hypothesis. The idea is that actual data are localized to sub-region or sub-manifolds in the latent space. So you have the vast latent space, but not every part of the latent space the data are not evenly distributed in this latent space, but they clock in a particular part, very small part of it. And these part form manifolds, sub-manifolds. That's the idea. The reason, or the possible reason, is that not all feature combinations are realizable. So if you have a kind of the image, image classification model, so you might find, so this is a kind of illustration that this is a kind of the manifold in the three-dimensional space that represent a possible image. So there's a horse here, and I don't know what it is. So lying on this submanifold, and if you are not on this submanifold, this is just a noise and so on. So the meaningful data lie on the submanifold. That's the idea. And this I think is a very familiar idea. For example, consider kind of trying to locate the cities on the Earth. And this is obviously constrained by the certain relationship that is that it should, every cities must be lying on the surface of the Earth. So it must be, every city must satisfy this kind of equation if you represent in a Euclidean space. So this is a possible city, but obviously this is not possible as a coordinate of a city, right? And the same thing, same idea is represented in the regression curve. The regression curve is supposed to specify the possible combination of X and Y here. So the idea is that it's possible, or here, but this is not possible, and so on. So this is the very kind of intuitive idea underlying manifold hypothesis. All right. So then what does it, how does it kind of relate to the functional constraint? Actually, functional constraint yields a submanifold. Well, think about the space. It might be a latent space. And think about the smooth function on the latent space. And then with this smooth function with certain conditions, you can create a submanifold. You can define the submanifold. Well, the detail is here, but the detail does not matter so much. So suppose that the function is from this space to real, well, it's a real valued smooth function. And for a particular value, its inverse image with under particular condition, define the submanifold. Well, this is the idea underlying the what we saw with the city locations, right? So the function here is x squared plus y squared plus z squared equals certain value that is Earth's radius. Then every point that satisfies this functional constraint must be on this sphere. So functional constraints give rise to a manifold. And this constraint turns out to be very important in generative models. So there are several algorithms to learn this data manifold, representation manifold. The most famous one is variational autoencoder. And turns out that it seems like they are learning this manifold. And if you learn this manifold, you can move the data point along on the surface of this manifold and create a new image. For example, this is a kind of the illustration, but suppose that this is the submanifold that represent the human face. And suppose that this is one point and this is another point, but then by dragging this point to this point, well, you can change the image gradually from the female face to the male face and so on. So it suggests that a successfully learned representation manifold identifies the concept of face, right? And by doing so, it allows for inductive reasoning because it is kind of extrapolation. So it asks a question, okay, so what if the image would be like if that person is female or male or wears a glass or something like that. So it's a kind of extrapolation, it's an inductive inference. So, and again, this dates back to the old concept of functional constraint and Casillas, the Casillas Funktionsbegriff. So he focused on the inductive rather than the descriptive or classificatory role of concept. And he said the genuine concept must, well, gives the kind of the universal rule for the connection of the particulars themselves. That is, that it must get kind of identify the concept, function that generate particulars. So function concept here is a rule that specify how its instance are generated. So what we have seen is that, well, from Boolean abstractionism plus functional constraint, we got conceptual lattice. And this conceptual lattice allows for material inference. And from the Euclidean similarity view, on the other hand, from functional constraint gives rise to representation manifold, and that allows for certain kind of data generation. So the functional constraints is very important in for inductive inference. And this functional constraints are represented on the one hand by lattice, on the other hand by manifold. So that was the first part. How much do I have? 10 minutes? 10 minutes, okay. Okay. And then lastly, I just go quickly, how to combine these two aspects. So how to embed, how to combine the algebraic structure, how to impose algebraic structure on the geometry. So that's a very important topic in the representation learning. And in the area of natural language processing or large language models, we have several kind of results here. For example, the word vector is known to have a certain kind of algebraic properties, like you can add and subtract words and so on. And there are several techniques to embed the hierarchical structure of words in the latent space using the certain like Poincar embedding and the box embedding and these things. Well, they create a lattice structure on the latent space and so on. So there are several techniques to impose hierarchical structure on the geometrical or the word representation space. But what it does is actually extract a rule that implicitly govern large language models material inferences, right? So, well, ChatGPT and so on makes the inference, right? So if you ask, well, it says, well, octopus is an animal is an organism, and so on. So if we can represent the word representation in terms of hierarchical structure, it is like the kind of making explicit of these implicit rules that the LLM is following with a certain kind of algebraic structure. So it is very much like Robert Brandam's concept of the Brandam's elucidative project. So the elucidative project is a making explicit what is implicitly done in everyday reasoning. So he says that, well, for example, logic, the modus ponens or something, it's not the rule we are following in the deductive reasoning. We are not applying the modus ponens when we reason. Well, we reason in an implicit way. And but modus ponens and the other logical rules that is not something like a reasoning engine that we follow, but just it's kind of the what makes explicit what we are doing implicitly. So the same thing applies here. The lattice is not the internal algorithm of LLM, but it just makes explicit what they are doing. So I think this is what we can do with constructing a lattice representation. But lattice representation primarily applies to LLM. And well, of course, well, the LLM use language as data. So the data itself has already a structure and the discrete and so on. So it's not so much surprising, maybe not so much surprising that we can have a lattice structure on the latent space. And the question is, can we do the same with the general deep neural networks? And the one problem here is that the aforementioned property that concept lattice is closed. The concept must be closed in the conceptual lattice. That is, the instance must be sharply demarcated by necessary and sufficient condition. And actually, from a mathematical perspective, given a complete lattice is the same thing as defining a closure operator. So the closeness is very interesting property, intrinsic property of conceptual lattice. But as Wittgenstein says, well, the concept is not demarcated sharply by the boundary. So what he says is actually the concept is not, well, in a topological sense, closed, but it is open. That is, well, I omit the particular detail here. So yeah. And also that problems show up in the actual problem, in the classification problem. The classification actually segments a representation space. But if Wittgenstein is right, there's no single correct way to carve up conceptual lattice from a representation space. As he said, you can draw a boundary, or none has so far has been drawn. So there can be several ways to segment representation space. And I think this is related to adversarial attack. Adversarial attack, as Jiji discussed yesterday, is, well, it adds a certain slight noise to image to make machines misclassify the object. And that one possible explanation of this is that the image is on the manifold, but if you add noise, it kind of detach the object from the manifold. Oh, sorry. So, and it kind of tries to, it's an attack. It's kind of exploit the edge of classification. So it is kind of the what Wittgenstein, the problem, did reflect the problem that concept is not closed, as Wittgenstein said. Okay, so the upshot is that lattice representation may help make explicit the implicit rule that governs large language models, but application to other deep learning model, deep neural network is, I think, still challenging. And there's inherent difficulties about this, how to reconcile the closure property of lattice with continuous data. So that is, I think, the fundamental difficulty here. Okay, the conclusion. So in this talk, I try to update the philosophical theories concept, abstractionism, and the similarity view. And in the important point is that functional constraints, and it gives rise to conceptual lattice with the capability of material inference on the one hand, and representational manifold with the capability of data generation on the other. So the functional constraint is the key for inductive inference. And the second, I talk about the reconciling the algebraic and the geometric aspect of concept. So in one respect, in the language model, maybe we can have a lattice representation, but the closure probe might be a problem for the other deep neural network in general. Okay, so that's it. Am I on time? Well, thank you.
Question.
That's very stimulating talk, Cheon.